Bless you. How's everyone doing today? Yay! It is Eclipse Day, and I'm excited. Any questions, needs, concerns, etc. before we get started? All right. So today is Eclipse Day. I'm very excited. As a reminder, there is no in-person lab this week, so that at minimum everyone is free. It doesn't have to be in a lab room for physics this afternoon if you want to be outside and observe the eclipse. The eclipse will hit as full as it's going to get for this region around 3:30. We'll hit about 75% totality. The process should begin around 1:30. Hit totality for us around 3:30, and then the sky should be back to normal by 4:30. If you want to view the eclipse, make sure you have grabbed a pair of these. I cannot stress again, don't stare at the sun or the eclipse with your bare eyes. So grab some of these eclipse glasses if you haven't already. Today what we're going to be talking about is eclipses in general, but also gravity, how gravity contributes to orbit, and therefore how orbit is responsible for the eclipse. There's not an in-person lab this week, but there is a remote lab, a very short assignment that will utilize the concepts and math discussed today. So that is currently posted to Brightspace, and I will email out a copy of it as well, and that is to be considered your assignment instead of an in-person lab this week. Sound good?
Is it due on Friday?
Officially, yes. Unofficially, I need it before grades are due. Any other questions before we begin? All right, so this will be drawing from material that is listed within chapters 9 and 10 of the textbook. Eclipses happen basically when one of our important stellar objects, the sun or the moon, gets blocked. You may have experienced some before. There was a solar eclipse about 7 years ago now, and then I think another one about 5 years before that. On Earth, we tend to have two different types of eclipses. The one today is solar in nature because the sun is what's getting blocked. But lunar eclipses happen when the moon gets blocked. Something has to pass in front of the object. For a solar eclipse, the moon passes in front of the sun. For a lunar eclipse, the Earth passes in front of the moon. Therefore, sunlight can't get to the moon to bounce off of it. Therefore, you can't see the moon. But the one today is a solar eclipse. The name is always which of the two gets blocked. Today's solar eclipse will be a total eclipse depending on where you are viewing it from. There is a path of totality that reaches from Mexico up to Maine, parts of Canada. If you're in this path, you will see a total eclipse. If you are not in that path, you will see a partial eclipse. Total eclipses, as the name suggests, have the moon fully in front of the sun. That does not mean that we get no light. It just means that the direct path is blocked. But it is possible, actually, for the moon to pass in front of the sun and not totally block it, and that's because the distance between the Earth and the moon is not always constant. So it's actually possible for the moon to be slightly further away and create an annular or ring eclipse instead. I don't remember if the 2017 eclipse was a ring eclipse, but the one that I think was summer of 2013 was a ring eclipse. So Whether or not you get a total eclipse depends on a lot of factors, namely where you are and how close the moon is to Earth at that particular day. But if you are in here, you're in the correct geometry to get a total eclipse for today. Otherwise, it'll be a partial eclipse. We are in this band right here, so again, we'll get about 75% totality, maybe a little closer to 80. And to better see what's happening from space, this is a simulation. And I'm going to actually cut the lights so you can see the shadow. There we go. Behold. That's a big shadow. Now, if you've experienced any sort of a solar eclipse before, you might have noticed that the sky doesn't go completely black. Sound familiar? Now, the sun itself does get blocked, and you can kind of see, I'm going to tab back to the first image again. Even when the sun gets totally blocked, you can usually see the sun's corona peeking around the moon. You can even see like prominences and solar flares. This is literally giant gouts of fire that burst off of the sun and arc back to its surface because of magnetism mostly. Because the sun is more than just the single ball of fire, it has an atmosphere that is also on fire. Blocking the physical sun doesn't stop all of the light, if for no other reason than the sun's atmosphere also emits light, but also because of the fact that light bends, especially once it hits our atmosphere. So even once this shadow is fully over the United States, we still get light bouncing into the dark zone from outside of the shadow. It's kind of like how the night side of the planet is never completely dark, even if the sun's totally not visible, because light bounces around the atmosphere from the day side of the planet. It's the same thing during the eclipse. Even if the sun was completely blocked, it would just look like nighttime because light would still be bouncing towards us from the parts of the planet that aren't blocked. So that's why the sky never, at worst, it would look like night, but in my experience, it never gets quite that dark. But it's pretty cool to see from space. This is the view that the space station astronauts would get, except they're a little too close to the, like, you'd have to be pretty far out to see this angle. This is a simulation. Questions? All right. Now, since physicists like math and numbers, we are going to today calculate the math and numbers responsible for gravitation and orbit, since those are the two things that are required to have an eclipse. We've already talked a bit about orbit. When we were doing rotational motion, I talked about centripetal force and how in order to cause one thing to spin in a circle around something else, you need some amount of centripetal force drawing the rotating object towards the center of its orbital path. Everything wants to move in a straight line, and force is required to kind of act as a leash to keep an object moving at a fixed distance around something rather than just shooting off in a straight line. I mentioned that this applies to the moon orbiting the Earth because the moon has mass and velocity, therefore it has momentum trying to get it to move in a straight line. We don't want the moon to rocket into space in a straight line. We need the moon for several reasons. So instead what happens is the gravity from the Earth on the moon acts as a centripetal force, again kind of metaphorically acting like a leash to keep the moon at a set distance from the Earth, just constantly moving in a circle. And this is good because we need the moon, again, for several reasons. The math for this that we've already covered is 1, centripetal force is equal to mass times centripetal acceleration. This is the mass of the orbiting object, by the way. So in this scenario, that would be the mass of the moon, which we do have an estimate for. So on the moon's mass, it has to have a certain amount of centripetal acceleration to keep constantly looping around the Earth. That acceleration is provided by some centripetal force. The force that acts as the centripetal force in this scenario is that of Earth's gravity acting on the moon. And this is a more direct formula for centripetal acceleration itself. In order to have centripetal acceleration, the moon needs to have some forward velocity, and it is being forced to start turning in a circle of radius r. And it is radius r. There we go. Earth, moon. The radius in question is going to be the distance from the center of the Earth to the center of the moon, and that's because that's the center of the gravitational effect. Earth's gravity is centered on the center of the Earth. The moon's mass and gravity is centered on the center of the moon, and therefore the center of the moon orbits the center of the Earth. So the r here, the distance between the two, is very specifically core to core. And we call it radius because it is the radius of the giant circle that the moon's motion creates. So when I call it radius, this is why. Sound good in review so far? Okay. Now, tapping a little bit forward, showing how these formulas get used when specifically calculating orbits. We've got centripetal force, centripetal acceleration, and the notion that gravity is acting as the centripetal force in space. Some force always has to play the part of centripetal force. There's never one thing that's always just centripetal force. It's like a part in a movie. Something has to play that role. Gravity is playing that role for us in space. So we tend to set gravity equal to centripetal force. Therefore, we can use Fg in place of Fc in this formula, and therefore we can derive an equation something like this. The force of gravity between the Earth and the moon is acting as a centripetal force on the mass of the moon, causing it to keep turning in a circle of radius r while it moves at linear velocity v. So that's just somewhat of the application of the formulas. How do you feel so far? Okay. Now, if we wanted to use this to calculate the orbit of the moon so that we could predict when future eclipses are going to occur, we would need to know the mass of the moon. This is it's a known constant. We've estimated the mass of the moon over the millennia. We need to know how fast the moon is moving. We need to know the distance from the Earth to the moon. These are things that scientists have spent a very long time researching and approximating. You can Google what their current values are believed to be, and I will provide those values for us in a minute. But for right now, you can just assume that those are known things. We know moon mass, moon velocity, moon rotational radius. My question for today is, how do you calculate the force of gravity between the Earth and the moon? Because the way that we normally calculate gravity in this class, Fg equals mg, where g equals -10, that's not going to cut it in space. Do you know why that won't cut it in space? It's okay, we're here to learn. Sorry? They're actually, okay, it's different, very good. There is most certainly gravity in space. I want to make it clear, gravity does not turn off when you leave the planet. We know that there's gravity in space because the moon needs gravity to orbit the Earth. If there was no gravity in space, the moon would just rocket away in a straight line. Similarly, there's gravity in space because the sun's gravity causes the Earth to orbit the sun. If there was no gravity in space, we would rocket away from the sun and then several more bad things would happen. There is most certainly gravity in space. It does not shut off once you leave the planet. The astronauts are not technically weightless. They have weight. There is a force of gravity acting on them, causing them to orbit the planet. But it's most certainly not the same level of gravity that you get on the planet. This value that we've been using for G, -10 or -9.8 if you want to be more specific, this is a very well-researched value for the acceleration of gravity on Earth's surface. This only works on the planet. Once you leave it, once you get too high up or even too far down, frankly, if you're burrowing to the core of the Earth, this number starts changing in either direction. This only works on Earth's surface. We kind of take that for granted sometimes. Meaning that physicists need a more generalized formula to be able to tell us gravity anywhere, not just on Earth's surface, because as it turns out, all masses create gravity on all other masses. So it's not just Earth creating gravity or the sun creating gravity, everything makes gravity, and we need a formula that will allow us to better estimate what gravity is everywhere, regardless of which masses you are examining. M times G doesn't cut it for that, and so physicists developed a different formula. It's a bit of a doozy. Are you ready to look at it? All right. We call this the universal law of gravitation. This is the formula that lets you calculate the force of gravity between literally any two things. Because all mass creates gravitational fields. Gravitational fields are literally a field, it's literally like a force field. It's just this field that matter gives off. All mass exerts a gravitational field warping space-time around it. Literally all mass, from single atoms all the way up to planets and black holes. And this formula allows you to calculate the force of gravity between any two masses, Earth and Moon, Earth and Sun, you and Earth, you and your cell phone, you and Pluto. As long as two things have mass, there is a force of gravity between them, whether it's big or minuscule. And what this formula tells us about that force is, the force of gravity between any two things is going to be equal to big G. It's not the same as little g, because uppercase and lowercase variables are typically different in physics math. Big G is this number. We call this the universal gravitational constant. You would never have to memorize such a thing. It's a very weird looking number. I would have this written on your formula sheet if you ever needed it. But if you ever see uppercase G in a formula like this, that is a constant 6.67 times 10 to the negative 11th, and then we gave it a unit so that the formula worked. But big G is always this. If you're ever using this formula, this is the number you plug in for big G. That's always the same. It's just a very specific value that we came up with that tells us kind of how gravity travels through space. You needed to understand how gravity, like adjust the values of gravity based on how it works through distance and space-time. So that's all it is. It's a very different constant to lowercase g. Bless you. Questions so far? All right. So, force of gravity between any two things equals big G times mass 1 times mass 2. This is why you need mass to create gravity. You need two different objects, each with their own mass measurement. And this formula tells you the strength of the gravitational force between the two of them. You cannot use this formula correctly with only one object. One object creates a gravitational field, but one object does not exert gravitational force on itself. It exerts gravitational force on a second object. So you need two things, you need two masses. Got them here listed as M1 and M2. Later on, I'll get more specific about which one is like mass Earth or mass Moon if I need to. But you need the two masses, and you also need to know how far apart they are. So divided by r squared, and it's using r in the same way we use it here. It's the distance between their centers of mass. And again, we call it r because it is technically the radius of the giant circle of gravitational field that the objects create. Every object, as long as it has mass, exerts a gravitational field out in all directions, and the r is the radius of that giant circle. So the r is how far apart the two objects' centers of mass currently are. This means that gravity, the strength of gravity, depends on the value of the masses and how close the two objects are. This is why that 10, that strength of gravity we're used to, only works on the surface of planet Earth. If you get further away from Earth's core, you're changing that value, and therefore you're changing the strength of gravity on you. If you get closer to Earth's core, you change this value, and therefore you're changing the strength of gravity on you. They actually used a variation of this formula to derive that 10. And again, this 10 is very specifically determined based on how far the surface of Earth is from Earth's core. So mass and distance both matter to gravity. That's why gravity gets weaker in space. It doesn't go away, it just gets weaker if you're going further away from the planet you came from. How do you feel so far? So, we got a brand new formula. Let's give it a little bit of practice and context. Let's say that we are going to take two 1 kilogram masses, so one of these and then a second one of these. I don't think I have a second one, so I'll have to get a little creative. Ah, I do have a second one. All right. Two 1 kilogram masses placed 1 meter apart. We are going to calculate the strength of the gravity between the two. Because right now, there is a gravitational pull between these two objects. Think of them as two different planets, and we're going to estimate the strength of their gravitational pull towards each other. Our formula, Fg equals big G times m1 times m2 over r squared. Fg, big G is 6.67 times 10 to the negative 11th. Again, that value is right here. You won't have to memorize it. It'll be on the formula sheet next to the formula. It should already be there. Yes, it is. Next, m1 times m2. You've got two 1 kilogram masses, so we're just going to input 1 kilogram times 1 kilogram. And lastly, r squared, distance between the two objects, squared. I placed them 1 meter apart, so that will just be 1 squared. Now, when you're using this formula in your calculator, you should usually be pretty careful. Not only is there a number with a times 10 exponent in it, you also want to make sure you are only squaring radius, and that the whole squared radius gets divided by everything else, or is divided into everything else. So you should always be very careful doing this one in your calculator. It's okay if you take it one line at a time. If you wanted to input it all at once, I would do that looking something like this. 6.67 e negative 11, open quote, open parentheses 1, close parentheses, open parentheses 1, divided by, open parentheses, squared, close parentheses. If you wanted to do it all in one line, it should look like that. Being very careful with the parentheses. 6.67 e negative 11, 1 divided by 1 squared. And the force of gravity you would get is 6.67 times 10 to the negative 11th newtons. On the grand scheme of things, do you think you can feel sorry. Do you think you could feel a force that size? No. That is too tiny. Yikes. Sorry. Pardon me. That force is far too tiny for a human neuron to detect. And I know you can't detect it because likely you cannot detect the force of gravity from this object changing as I move it around the room. A mass this size is always going to give off gravity of about this scale. It's teeny. You'll never detect it. Now, if we left these two things alone in the vacuum of space for thousands of years, they would slowly start drifting closer to each other because the force isn't zero. It would just take a very long time for the acceleration to start becoming noticeable. But on Earth, where you've got friction all over the place and also bigger forces of gravity, you're never going to notice a force this small affecting things. I don't even know if that would be enough force to make one of your arm hairs twitch. So, most gravitational forces are fairly negligible. All right so far? Okay. Now, before I move on to a different problem completely, I'm going to do that thing where I show what happens if you change one or two things to see how that affects the formula. First up, what happens to the force of gravity if you double one of the masses? Let's just say I take mass 1 and double it to create 2 kilograms. What does that do to the final answer? It doubles it. If you have twice the mass, you exert twice the gravity. Therefore, very big objects like the Earth create a lot of gravity. If you cut that mass in half, what's going to happen to the answer? Halved. Yeah. So gravity, the strength of gravity correlates directly to the mass of the object. More mass, more gravity, and that is why if you went to Jupiter, you would be crushed flat. Also, Jupiter doesn't really have a surface to stand on, so space is dangerous. All right. Now, instead of changing mass, what happens if you change radius? What would happen to the number if you doubled radius? These objects were twice as far away from each other. Again, you shouldn't be erasing anything. I'm just going to show you what happens to the final calculation. It drops rather substantially from 6.67 to 1.67. It was cut down by 1/4. If you go twice as far away from something's center of mass, gravity is reduced to 1/4. If you get further away from something, gravity decreases. Because you are further away from its center of mass, it has less pull on you. And that is why gravity gets weaker when you leave Earth. It doesn't go away. The astronauts still weigh something. The moon still weighs something. But the further away you get, the weaker that gravity gets until eventually it's negligible once you get far enough out. This is why you would never detect or frankly, why you don't really notice the sun's gravity acting on your body. The sun's gravity is very strong, but it's very far away from our teeny masses. Therefore, you don't really detect the force from the sun as you rotate around the Earth all day. Like, I can't tell just from gravity what direction the sun is in because it's too far away from me. Same with Pluto. But to note, double the radius, force gets cut down by 1/4. If you cut radius in half, the reverse of that would be quadruple the force of gravity. And that's why gravity gets stronger if you burrow to Earth's core. We don't really do that for several reasons. But if you managed to get closer to Earth's core, gravity would increase. And that's why pressure increases when you burrow into Earth's mantle and core. The gravity and pressure is so strong down there, it's literally enough to melt all of the rock, and that's why the mantle and the core are molten. And why you get high enough pressures and heat levels down there to make things like diamonds. Basics of the formula feel okay? All right. So that was kind of just to calibrate the formula. Now let's do a space type calculation. Let's start using the masses and the radii that you would actually see in space. We're going to use this formula to calculate the force of gravity between one 75 kilogram human being and the Earth beneath their feet. I'm going to add a human to my very poor drawing of the planet. We need the mass of these two things. We're going to use 75 kilograms for the mass of our human. And for the mass of the Earth, scientists have spent a very long time trying to estimate this. Currently, we use 5.98 times 10 to the 24th kilograms. And then for R, since the human is standing on Earth's surface, that human will therefore be, considering that their center of mass is, there. I just drew the person very big for dramatic effect. If they're on Earth's surface, the distance between their center of mass and Earth's core is the radius of the planet, which is currently estimated to be 6,378,000 meters at the equator. And we're going to take that big old radius and square it. Once again, you want to make sure to be very careful if you're putting this all into your calculator in one line. I would do open parentheses 6.67 e negative 11 close parentheses open parentheses 75 close parentheses open parentheses 5.98 e 24 close parentheses division sign open parentheses 6 e I'll just do the whole thing. 6378000 squared close parentheses. And if you input all of this into your calculator correctly, what is the force of gravity from Earth on this person? I've got approximately 735-ish newtons, which cosmologically speaking isn't a lot. That is the force between the Earth and one human standing on its surface. But I want to point out that that is about, it's supposed to be the same number you would get if you use our other method of finding out how much something weighs on Earth's surface. Remember, all semester for weight on planet Earth, we've been using mg. So if I do this really quick with 75 kilograms and the slightly more accurate value of 9.8 as opposed to 10, 75 times 9.8 gives us a force of gravity of 735 newtons down. Hey look, the formulas match. That's on purpose. Again, this value for G, we rounded to 10 for the most part in this class, but I used the 9.8 so it was closer to the other number. This number was derived from all of this, very specifically. Questions? Feeling all right? All right, a couple small notes about this number as we've calculated it now. This number depends on the mass of both entities and also the distance that you are from Earth's core. You are technically able to manipulate that distance on planet Earth in a couple of different ways. If you wanted to be lighter, you could get yourself further away from the core. And technically standing on the equator is one of the best ways to do that. Because as it turns out, the Earth isn't actually a perfect sphere. The Earth is a little bit more elliptical. Not a whole lot, but technically it's a bit wider at the eclipse. Not the eclipse, wow, wrong E word. At the equator. The Earth is a little bit wider at the equator. Therefore, if you're standing on the equator versus the North Pole, you are slightly further away from Earth's core here than here. Therefore, you are lighter on the equator than you are on the North Pole because you are further away from the center of the Earth. It's about 20 kilometers difference, which I don't know if there's a mountain any bigger than 20 kilometers, so that might actually be your best bet if you want to keep your feet on solid ground. Just go to the equator. Or better yet, find a mountain on the equator. I can't think of any off the top of my head, but surely there's some.
You weigh less though or something?
Very slightly, very slightly. You might not notice it, but it's there. And if you want to really try to cut down on that number, you'll start climbing really tall mountains and going on hot air balloon rides to the upper atmosphere. Bring oxygen tanks. That said, you have to get really far away from Earth to start noticing a difference. At the height the space station is, again, this 9.8, this 10, is calculated for Earth's surface. At the height of the astronauts, which is about here, it only drops to 8. They are still accelerating because of gravity with a level of 8 rather than 10. And that's this far away. There is very much gravity in space. And that's why things fall out of the sky. Second related question. This is how much a human weighs on Earth. Counterpoint, how much gravity does the human exert on planet Earth? Because there's always an equal and opposite force. The quirk with this formula is that the force you calculate from it goes both ways. Object 1 exerts gravity on object 2. Therefore, Newton's third law dictates object 2 exerts the same amount of force back on object 1. If this person weighs 375 newtons on planet Earth, therefore planet Earth weighs 375 newtons on planet this person. However much you weigh, you are exerting that much gravity back on the planet. Likewise, however much the moon weighs at its current orbital position, it exerts gravity back on the planet as well. This formula is always two-way, inwards two-way. This object is pulling this object towards it. This object is pulling this object towards it. It's not one or the other, it's the same on both. The only reason that the moon doesn't actually pull the Earth any closer to the moon is just because the Earth is hundreds of times more massive than the moon. Therefore, the force from the moon back on the Earth isn't enough to make the Earth visibly move. But it's still there. And we know it's there because it causes the tides. Actually, I suppose if you really wanted to be as light as possible on planet Earth, you'd stand on the equator and you'd want the moon to be right overhead, because then the moon's gravity is pulling you upwards with the tides. You'd also want the sun to be right overhead. So you'd want to be on the equator and you'd want a solar eclipse to be happening straight overhead. Good luck with that. Questions? How are we feeling? All right, a couple of points to summarize and close us out. This is one extra formula that we have access to help understand the gravity centripetal force relationship. So I'm giving you this. You should write it down so that you can use it in your take-home lab this week. This, I call it the orbit equation. This is literally the gravity equation equals the centripetal force equation. In space, gravity is acting as the centripetal force causing orbit, therefore they have to be equal to each other. So this here is just the two equations stapled together. On the left side, you have the gravity equation, g(m)m over r squared. On the right side, you've got the centripetal force equation, mass times velocity squared over r. I've been a bit more specific than just saying m1 and m2 though, because I want to make it clear that there's a mass that will repeat between the both sides, and that is the mass of the satellite. Satellite meaning the thing doing the orbiting. The moon is a satellite of the Earth. Our satellites are satellites of the Earth. So if you were using this for the Earth and the moon, to say calculate the moon's orbit, like you will in your take-home lab, you put Earth's mass there, the moon's mass there, and then the moon's mass here again. You need both masses on the force side of things because you need two masses to have a gravitational force. But on the centripetal force side, you reuse the moon's mass because the moon is the thing doing the orbiting. The moon is the thing doing the centripetal accelerating. Is that clear the way that I've labeled them? And your take-home lab will have you use all of the equations shown today in a very laid out logical pattern. I've asked a series of questions such as use the formula with these variables to calculate the force of gravity, use the next formula to find centripetal force and acceleration, and then calculate how far the moon is away from the Earth in a specific sequence using these formulas. So I try to lay it out, and I encourage you to ask me questions at any time as you are working on it this week. I won't have office hours this afternoon because I'm going to watch the eclipse, but you should email me anytime you have questions, and you should also find me in the building any day except this afternoon. But to summarize, this is all very important because we do need to know where the moon is. It affects our orbit, it affects a couple of interesting things such as the tides and also which meteors are going to hit us, because the moon does kind of shield us from a lot of meteors. Sometimes they hit the moon instead of us, which is useful. So we need to know where the moon is, and therefore we do all this math to predict where it's going to be next. It's also important to do this math because we need to keep tabs on how far the moon is away from us, because it's drifting away very slowly over periods of millions of years, but it's technically happening. And so we need to keep tabs on that, because if the moon leaves, we lose the tides, and we need tides to keep the ocean from dying. Just to review again, if I didn't say it very loudly. The moon exerts gravity back on the Earth. That gravity is not enough to move the mass of the planet, but it is enough to move the oceans, since the oceans are fluid. So the position of the sun and moon affects tides, and that's why we need the moon. If the tides didn't exist, the oceans would just sit stagnant like a lake, and they would die, because you need the tides and the currents to keep everything moving, or else they go stagnant like a pond or a puddle can, which is bad. I guess we have questions? All right. I like all this stuff, so thank you guys for listening to my talking about space all day. The very last trivia fast fact I'm going to throw at you is if you take this formula and you shrink the radius down to something far too small, you make a black hole. Black holes happen when the radius gets too tiny, and therefore the gravity gets too big, and it starts warping reality. Gravity warps reality. So we'll end on that note. Let me know if you have any questions about any of these concepts or on the take-home lab. On Wednesday, we'll talk about sound, and then we'll head into test review territory, which you're all ready for next week. Please have a wonderful day. Please have a wonderful eclipse. Viewed responsibly through eclipse glasses. And have a great day.
What happens if you use sunglasses to look at it?
You will burn yourself, the same way you would if you just stare at the sun normally through normal sunglasses. See, the real danger with eclipses is because they are dimmer than the sun, you think you can stare at them for longer. But that doesn't, the moon doesn't really block all of the infrared space radiation that will burn your retinas out without you noticing. You too.
How do I get there?
You too. Thank you.